Hello everyone, I'm Gurjeet Singh and I'm starting making a video on class 10th, chapter 10, light reflection and refraction. Now, here is we come to chapter number 10. What we see a variety of objects in the world around us is because of light. We are not unable to see anything in a dark room. On lighting a room, things become visible. What makes things visible during the day? The sunlight helps us to see the objects. An object reflects light that falls on it. This reflects light when received by our eyes enable us to see the things, and we are able to see through a transparent medium as light transmitted through it. The things we have recollected from this is that one will need light, and second, it should be with a transparent medium. Okay. Now, there are a number of common phenomena associated with light, such as image formation by mirrors, twinkling of stars, the beautiful colors of the rainbow, bending of light by the medium, and so on. Image formation by mirror is just an application, but while this image formation is principle, but while the twinkling of stars, beautiful color of rainbow, bending of light by a medium, these are all the applications depending on the properties, what we learn from this chapter. This chapter is divided into two sections, the light reflection and refraction, and the second, chapter number 11, is basically depends on the application of light, that is the human eye. In this chapter, we will study the phenomena of reflection, refraction of light using a straight light, propagation of light. These basic concepts will help us in the study of some of the optical phenomena in nature. We shall try to understand in this chapter and the reflection of light by the spherical mirrors and the refraction of light and their application in a real life situations. Now, reflection of light is nothing but the highly polished surfaces. When you see a mirror, a plain glass is in front of it. It is so that the light enters to it. It gives a reflection, but certain bending of light to the medium should be there so that it can be visible to us. That's why a mirror has been placed on a polished surface, or polished has been done on a back of a plain mirror, transparent glass, right? So you are already familiar with the laws of reflection of light. What are they? First, the angle of incidence is equal to the angle of reflection. The incident ray, the normal to the mirror at a point of incidence, and the reflected ray all lie in a same plane. These laws of reflections are applicable to all type of refracting surfaces, including the spherical surfaces as well. So the image, you are familiar with the formation of the image by a plane mirror. What are the property of an image? The property means how the image is formed, virtual or real, erect or inverted. So the image is formed by the plane mirror is always virtual and erect. The size of the image is equal to that of the object, and the image formed by the plane mirror is as far behind the mirror as that is in the front of it. But the further the image is literally inverted. How would the image be when the reflected surface are curved? So to understand this, we can see an image in a spoon as well. It is in a day-to-day thing we are using. So the activity 10.1 is basically based on this only. And the further, after discussing this activity, that how the image is formed in the mirrors in the both side of the surfaces, spherical surfaces, what is the image formation? Now 10.2 is spherical mirrors. Now spherical mirrors are of two types, concave mirror and convex mirror. The reflecting surface, what is it? The reflecting surface of a spherical mirror may be curved inward or outward. So a spherical mirror or reflecting surface is curved inward, that is faces toward the center of the sphere. Means if we make a sphere of it, it has some center, somewhat here. The reflecting surface is this. Now it faces towards the center of the sphere is called concave mirror. It doesn't mean that this is a concave mirror. No. Though it has the facing is towards the center, but that is blur part, the shaded part. The reflecting surface should be inward, and it should be faces with the center, towards the center of the sphere. Then it is called to be as a concave mirror. Right. A spherical mirror whose reflecting surface is curved outward is called convex mirror. The schematic representation of these mirrors is shown in 10.1 A and B. You may know that these diagrams that has a back of the mirror is shaded, this shaded part. Now to go further, the spoon जो उनसे उसका पर्च पार्ट है इनवर्ड और आउटवर्ड, that is the inward part is concave mirror and outward part is the convex mirror. Now to go further, we have to know and have knowledge of a few terms: pole, center of curvature, principal focus, focal length, radius of curvature, right, and aperture. Now these terms are commonly used in the discussion about a spherical mirror. The center of a reflecting surface of a spherical mirror is a point called the pole, and it lies on the surface of a mirror, and the pole is usually represented by a letter P. The reflecting surface of a spherical mirror forms a part of a sphere. The sphere has a center. It is obvious that when we have a circle within a radius, it should be have in a certain center. Sphere also has in a center. When we measure the volume or a surface area of a sphere, it is done by the radius. That's why it should be having a radius of curvature. Every curvature has its some radii. So in this way, that the spherical mirror also have a radius of a curvature. So this point is called the center of the curvature of spherical mirror, and it is represented by letter capital C. Now note that the center is not a part of a mirror. It lies outside the reflecting surface. The center of the curvature of a concave mirror lie in front of it. However, it lies behind the mirror in case of a convex mirror. As we can see in 10.2, the radius of curvature that C in the convex mirror, it is behind the reflecting surface, and in concave mirror it is in front of the reflecting surface. The radius of a sphere of which the reflecting surface of a spherical mirror forms a part, it is called the radius of a curvature of a mirror. It is represented by a letter R, and you may note that the distance PC is equal to the radius of curvature. Imagine a straight line passes through a pole, and the center of the curvature of a spherical mirror. This line is called as a principal axis in both the cases. Now we have an activity 10.2. It is based on that the light is at infinity from the sun, and a concave mirror has been taken and focused on the center of it, right? And the further next paragraph is all about the detailed discussion of an activity 10.2 and an answer of the last point in an activity. When it comes to the last paragraph, it is that it explains the figure 10.2a briefly. So it is a number of rays parallel to the principal axis falling on a concave mirror, and observes that the reflected surface, they are all meeting and interacting at a point on a principal axis of a mirror. This point is called as the principal focus of a concave mirror. Similarly, the reflected surface appear to come from a point to the principal axis. This point is called the principal focus of a convex mirror. So what we have here is interacting surface. The reflecting surface, reflected ray has come and interacts at the principal axis. That point defines as the principal focus of the mirror. The principal focus is represented by the capital letter L, F, and the distance between the pole and a principal focus of a spherical mirror is called the focal length, and it is represented by the letter small f. Now the reflecting surface of a spherical mirror is pi and a large spherical. The surface and then has a circular outline. The diagram of a reflecting surface of a spherical mirror is called its aperture. Like here we have defined all the terms: the ray, mirror, pole, focus, center of curvature, and now it comes to the aperture. The diameter of a reflecting surface of a spherical mirror is called its aperture, and the distance, which is shown in 10.2, it is called as mm, represents the aperture, mm. Now such spherical apertures, spherical mirrors whose aperture is much smaller than its radius of curvature, right, in this chapter. Now, is there any relationship between the radius of curvature and the focal length? Yes. The spherical mirror of small apertures, the radius of curvature is found to be equal to the twice of a focal length. That means the capital R is equal to 2 small f. This implies that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. Okay. Now let's come to the image formation by spherical mirrors. The activity all the activities which is discussed in chapter this we discuss at the last. Okay, now certain representation rules are discussed here. They are of four types. What are they? First is the ray parallel to the principal axis after a reflection will pass through a principal focus in case of an concave mirror or appear to diverge from the principal axis in case of an convex mirror, as it is illustrated in figure 10.3 A and B part. As it then when the ray is coming from far away, from infinity, and it touches the reflecting surface, it passes through focus, always principal focus in the case of concave mirror. When it comes to the convex mirror, we have the image, the object or light source comes from the infinity, touches the reflecting surface, reflects or diverges the path of a light, and the path is just associated with the focus only. It diverges from the principal focus, and the C is normal. That C draws a line normal to the reflecting surface and divides the angle into two equal parts, in two equal angles. Okay, in this case also it has the same thing. Now second part is same as it is to the first, but the thing is that it is from the downward, right? Means the light coming from either sides of the mirror, from upper side or a lower side, but parallel to the principal axis, it follows the same rule as it is in 1. But the third rule says a ray passes through the center of curvature of a concave mirror, center of the curvature of a plane mirror. In the direction of or directed in the direction of the center of a curvature of a convex mirror after the reflection is reflected back along the same path. This is illustrated in figure 10.5 and B. The light ray comes back along the same path because the incident ray falls on a mirror along the normal of a reflecting surface. Now this is also implies on this, means as it divides into two equal angles because it is normal. Now fourth part is the incident ray obliquely to the principal axis, obliquely towards the point P, that is the pole of a mirror, on a concave mirror or a convex mirror, is reflected obliquely. The incident and the reflected ray follows the law of reflection and a point of incidence, making equal angles with the principal axis. I is equals to R. An image formation by a concave mirror. What is it? Now, the mirror P is a pole for mirror, focus is a focal principal focus, C is center of curvature, M and N is the diameter, that means the aperture of the mirror. Now we have concave mirror here. There's a sixth part of it. Now here I'll tell you one method to learn the things. Okay, how these 6 diagrams. How? As it is the relation between the object and the image formation. Right? Now, as we go further, we'll understand it very clearly that the image is at infinity. Light reflects and passes through the focus from either side of the principal axis. So image is at far infinity, the image formed is at focus. Right? This is the first point. Second, as the image comes closer somewhere at beyond C, means beyond the center of curvature, it reflected from the surface and passes through focus. And now we have C, center of curvature. The ray passes from C and reflects on the surface and reflected back. The image form is what? Inverted. Inverted. It's beyond C, right? So it's beyond between C and F, means first one is at focus and other one image is formed beyond F, means between C and F, means it is going away from the mirror. Now in third point, when it comes the image, the object is at C, it reflected from the surface and passes from the focus and go beyond it. And when the object is lying on the C, it passes through the focus as well and go from this part. And the things is like the object is formed at C only. The image is formed at C only, and it is real and inverted. Now till here that as the object comes closer to it, the images go away from the mirror. It's between C and F and it is at C. Now in third point, when the object is between C and F, it reflected and passes from focus, and it makes the light passes from the head to this mirror reflected back and make an image beyond C, and it is also real and inverted. Now the third point is done, fourth is done. Now it comes to fifth image. It is when the object is at focus, reflects and passes through focus, and the C is just reflecting the light as it is. Now the object is at focus. Now the image is formed at infinity. Now the A part and C part is easy to learn, that when the object is at infinity, the image is formed. When the object is at infinity, the object is formed at F. And when the object is at F, the image forms on the at infinity. Now the last point is fifth one. Here every student get confused because we have they just consider first 3 points of a representation of or a formation concepts. The fourth one is used here. What is that? When it comes between P and F, the F is not included into it. right? So what the students mainly make a mistake here is they make like this one and it passes from this. Light cannot cross you. If you come in front of a spherical mirror and you come closer as between focus and the pole, it would be like just it not cross you. It will not passes from the focus, the ray, right? So what to do that it passes from the pole and goes down and divides the into two angles. The principal axis divided into two equal angles, and the upper one it passes from the center of curvature, and it's make an image of virtual and erect and behind the mirror. Now, uses of a concave mirror. It is commonly used in torches, searchlights, vehicle headlights to get a powerful parallel beam of light. They are often used as a shaving mirror to see a large image of a face. Even the doctors, even the dentist uses it to see a large image of a teeth of a patient. Right? Now the large concave mirrors are used to concentrate the sunlight to produce a heat in a solar furnaces. Now image formation by a convex mirror. That is B part. First part we have done the image formation by concave mirror. Now it's come to the convex mirror. Convex mirror have only two parts. What are they? It represented in the figure 10.8. What are these? When the image is at infinity, the rays come and reflected back and diverges associated to points with F. Diverges along F. It means the image is formed at F and it is behind the mirror. Okay, and the image is virtual and erect. The second point, when it is between the pole and the infinity and pole, the image object is at. It's found anywhere beyond the P or between them. It forms the same image, diminished and virtual and erect. What is the method to make it? As it passes, first it light comes, reflects from here with focus. Right. I make it large here. What are these? This one. It is this way. It is passes and crosses the focus. And the C is just making a half of these angles. Okay. Now this line is just reflecting back from C and it makes an image that is diminished, virtual and erect. A dash, B dash. Okay. Now it comes to the uses of convex mirror. Convex mirror is used in a rear view mirrors in the vehicles, right? These mirrors are infitted in the side of the vehicles, enabling the driver to see the traffic behind him, her, to facilitate the safe driving. Convex mirrors are preferred because they always give a erect, though diminished, image. Also, they have a wider field of view as they are curved outward. Right? So this convex mirror enables the driver to view much larger area than would be possible within a plane mirror. right? Convex mirror we have discussed here. Now we have sign convention, often enlarged for spherical mirrors. In it, we use a Cartesian sign conventions. What are the Cartesian sign conventions? This has been of 5 points. What are they? First is the object is always placed on the left side of a mirror. It doesn't mean that it should be concave or convex. It's always placed on the left side of the mirror. Always. That the light from the object falls on the mirror from a left hand side. All the distances parallel to the principal axis are measured from the pole of the mirror. This pole of the mirror. All the distance measured to the right of the origin, that means x-axis, x plus, are taken to be positive, while those on the left of the origin are taken as negative. The distance measured perpendicular to and above the principal axis are taken to be positive, and the fifth one is the distances measured perpendicular to and below the principal axis are taken as negative. Done. Now we have mirror formula and the magnifications. Now mirror formula, to have mirror formula, we have in spherical mirrors the distance of the object from its pole is called the object distance, and the distance of the image from the pole of the mirror is called image distance. And you already know that the distance between the principal focus from the pole is called the focal length. This is the relationship between these three quantities given the mirror formula, which is expressed as 1 upon V plus 1 upon U is equal to 1 upon F. Alright, now after this we have magnification. Magnification is height of the image, that means h dash, upon height of the object, that means h. That means m is equal to h dash upon h, and when it comes to the magnification related to the object distance and the image distance, it is expressed as magnification m is equals to h dash upon h, that means minus v upon u. And now note that the height of an object is taken to be positive, as the object is usually placed above the principal axis, and the height of the image should be taken as positive for the virtual images. However, it is to be taken as negative for the real images. The negative sign in the value of magnification, mark these lines, the magnification, the value of the negative sign in the value of the magnification indicates that the image is real, and the positive sign in the value of magnification indicates that the image is virtual. We discussed these examples in next few classes. Now it comes to reflection, refraction, reflection we have done. Now it's come to the refraction of light. Refraction of light are the certain things we have discussed saying here in few minutes, that is that in a glass prism, bending of pencils, and when we partially immersed in the water, Now, here are certain examples of that when a thick glass slab is placed over now some printed matter, the letter appears raised when we view through the glass slab. Why does this happen? When you have seen a pencil partly immersed in water in a glass tumbler, it appears to be displaced at an interface of air and water. But you might have observed that a lemon kept in a glass tumbler appears to be bigger than its actual size when viewed from the side. How can you account for such experiences? Right, so it is due to the refraction of light. Right, now let us consider the case of an apparent distance of the pencil partly immersed in the water. The light reaching you from a portion of a pencil inside water seems to come from a different direction compared to the part above the water. This makes the pencil appear to displace at an interface, and for similar reason, the letter appears to be raised when seen from a glass slab placed over it. So does a pencil appear to displace in the same extent if instead of water we use liquid like kerosene or turpentine? Will the letter appear to raise to the same height if we place the glass slab within a transparent plastic slab? You will find the extent of an effect for a different pair of medium. These observations indicate that the light does not travel in a same direction in all the medium. It appears when they traveling obliquely from one medium to the other. Mark these lines. The direction of the propagation of light in the second medium changes. This phenomena is known as refraction of light. Okay, now this is the application we have discussed. What is it? But in 10.3.1 we have refraction through the rectangular glass prism. What is it? Now we discussed activity 10.10. What is it? Fix the white sheet on a drawing board using a drawing pen. Now place a rectangular slab over a sheet in the middle and draw the outlines of a glass slab with a pencil. Let us name the outlines as A, B, C, D, as in figure 10.10. Now make 4 identical pins, right? Take 4 identical pins, fix 2 pins, say E and F. Not E and F. Don't do it as this way. Now make a normal of it. N and dash. As it I see, do it. N and dash. With a dashed line. Draw an angle somewhat at 18 to the normal, right? And draw a line from normal, that this should be the base, N and dash to be the base, and O to be the center of the protector, and N is at towards the 0 of a protector, and make increment of angle to 18, somewhat 18 or a 45. Let it be 45, right? Now place 2 pins, fix 2 pins at E and F, and draw. You have drawn line and place any 2 pins and make a mark around it, circular mark. Now place the slab again and just see these 2 pins and take 2 other pins and fix these 2 parallel to the light comes across the glass slab and fixed D2 pins and named it as G and H. As I am saying, do it like that only. And after placing it, it should be just like that, that the fixing with when you are fixing these two pins G and H, it should cover E and F properly, that it just come in front of them. That means the light is covering it. Now mark these two lines, 2 points which you have fixed. Now G and H. Now remove all these pins. Now fix G and H line, make a draw line and passes through the edge of the glass slab CD. It should touch, crosses, intersects with it. Now at the intersecting point it has O dash, and the normal of the normal, draw a normal which crosses CD and passes O dash, that is M dash, right, and join O and O dash also. Now E and F are incident rays, O to O dash is refracting ray, and G and H are the emergence ray, right, emergent ray. Now this has been done. Now E and F passes touches O. Now draw a line straight within a scale, and it is P. Okay, let it name it as P. So that line goes, that shows a lateral shift. It shows that the light refracts in the medium. Okay, the outside is air, this is glass, and this is also air. So light comes and it bends towards the normal, and it touches, and when it comes out of a reflecting surface, it goes away from the normal. Okay, now in this, the angle of incidence is by I, angle of refractive index is by small r, and refractive, and angle of emergence is with by C. And this example shows that angle I is equals to angle E. That is the law of refraction. Okay, now here are the laws of refraction of light. What are they? These are the incident ray, the refracted ray, and the normal to the interface of two transparent medium at the point of incidence all lie in the same plane. That is first law. Second law is the ratio of sine of angle of incidence to the sine of angle of refraction is constant for the light of a given color and for the given pair of medium. This law is also known as Snell's law of refraction. Okay. Now, what is refractive index? A ray of light that travels obliquely from one transparent medium to the another within a change its direction in a second medium. The extent of change in the direction that takes place is given pair of a medium may be expressed in the terms of refractive index, that the constant appearing on the right hand side in equation 10.4. Now the reflecting surface can be linked to an important physical quantity, that is the relative speed of propagation of a light in a different medium. We can say it as that the reflective index is just a relative speed of propagation of light in a different medium, and it turns out the light propagates within a different speeds in a different medium. The light travels fastest in the vacuum within a speed 3 into 10 raised to power 8 meter per second. In air, the speed of light is only marginally less compared to that in the vacuum. It reduces considerably in the glass or water. The value of refractive index of for a given pair of medium depends upon the speed of light in two mediums as given below. Now how we can write it as we have discussed or represented in equation 10.5. How it is that the light traveling from medium 1 into 2 as shown in figure, let the v1 be the speed of light in air and v2 light the speed of light in medium 2, that means glass. Now refractive index of medium 2 with respect to 1 is given by the ratio the speed of light in medium 1 and the speed of light in medium 2. ये रेशियो में होगा. This is usually represented by the symbol n subscripted by 1, right? And this can be expressed in an equation form as that n subscripted by 1 is equal to speed of light in medium 1 upon speed of light in medium 2 is equal to v1 upon v2. That's it. Now by this same argument, the refractive index of the medium 1 with respect to the medium 2 is represented by n subscripted by 1, 2. It is given by n upon 1 by 2 is equals to speed of light in medium 2 upon speed of light in medium 1 is equals to v2 upon v1. Right? Now further, if a medium is in a vacuum or a air, then the refractive index of 2 is considered to be with respect to vacuum. This is called the absolute refractive index, and it is represented by the n c or ng, we can say. If the c is the speed of light in air and v is the speed of light in a medium, then the refractive index of a medium nm is given by c upon v, that speed of light in air upon speed of light in the medium. Now certain the absolute refractive index of some material has been given in the table 10.3. Air, ice, water, alcohol, kerosene, fused quants, turpentine oil, benzene, crown glass, Canada Belgium, rock salt, carbon disulfide, dense flint glass, ruby, sapphire and diamond. Now glass is of two types, crown glass and flint glass. When usually it is when we have questions which is not defined that what is the refractive index it is not defined that glass has a refractive index of this, or not defined that it is a crown glass or an open glass. We usually take the value of a crown glass only. Okay, so that's to be considered. Usually we take 3 to 4 values of this table that we should learn is air, water, alcohol, kerosene, crown glass, and the diamond, and somewhere film glass also. That means at least 7 values we need to learn or to memorize it. Now it is for the further detail, not detail, it is just related to the refraction only. That is the ability of a medium to refract light is expressed in the term of an optical density. Now density is what? Dense hona. But optically dense means it is not the same as mass density. We have been using the term a rare medium and denser medium. Rare mediums means that the components, how the medium has been made or has constituted, the particles are densed or not densed optically, right? In this chapter, it is actually means the